Okay, so to finish, turning forces, first of all, and then a very quick look at power, right? Very quick look at power. So now, okay, so turning forces, let's have a look, right? If I have an object, rigid object, okay, and if I hold it here, so it's free to rotate, okay, if I apply a force here, okay, it doesn't go in linear motion, okay, it rotates, okay, it actually goes in circular motion, right? Okay, it rotates, okay, and we call that a moment or a turning force, okay, so it's a moment of force or turning force, okay, so I'm going to call it a moment from now on. Nothing to do with momentum, a moment, okay, right? Now, let's figure out what's the story, okay, right? Obviously, the moment depends on the magnitude of the moment, depends on the force, okay, and it depends on the distance from the turning point, because if I apply the force here, okay, right, the same force will not give you the same moment. You'll get a greater moment the greater the distance, right? Okay, that's why door handles are far away from the hinge, okay, so the hinge is the turning point and the door handle is far away, right? Now, so basically, let's have a look. So all we have, okay, it's quite straightforward really, okay, we have the distance from the turning point. So the turning point, also known as the fulcrum, okay, so it's a rigid body, so it rotates, and the moment, sometimes called m, but I'm just going to leave it as moment all the time, is the force multiplied by the distance, okay. So the unit is the Newton meter, okay, which is the same Newton effectively as energy, but it's just, that's coincidence. It's Newton meter. It doesn't have any special unit, so we call it the Newton meter. That's it, right? The greater the force, the greater the moment. So directly proportional. If I double the force, I double the moment. If I double the distance from the turning point, I double the moment. Okay, they're both directly proportional. That's it. That's moment. Okay. Now, there's a second scenario that we have to watch. Okay, is if you have, if we change it and we put the turning point about the center here. Okay, so in other words, if I connect it like that, okay, and if you think about it, this is a bit like the handlebars of a bike, okay. Now, if you want to turn right on a bike, you apply two forces, okay. So it's your handlebar and it's the center, okay. If you want to go that way, okay, you're going to basically apply a force this way and apply the other force back towards me, okay. So you're going to rotate. So you're going to apply two forces. So watch, two equal forces in opposite directions, okay, and effectively that has a turning effect only. It has a turning effect only. It causes it to turn, okay. So that is called a couple because there's two forces, okay. It's also called a torque, okay. So you have your definitions, okay, and to get the moment of the couple, okay. So moment of force, moment of the couple. Okay, it's force by d again, but this time it's the distance between the two forces. Or if you think about it, it's this force, it's force by the distance to here, plus force by the distance to here. Okay, it will be the same thing. Okay, again it's Newton meter, it has a turning effect only, it's the moment of a couple. This is the much more, the one you'll be dealing with a lot, because you deal with this in the experiment, okay, and we deal with it a lot more. Okay, so remember, you have to have a rigid body, you have to have a turning point, okay, a point that the rigid body can turn about. Okay, if I apply a force, it causes a turning effect, okay, and the moment of the force is found by force by distance. The second scenario is if you put the turning point in the middle, okay, of the rigid body. If I apply a force, you apply a pair of forces or a couple of forces, one down here, one up here, as you would on a handlebars of a bicycle, as you would on a tap, as you turn a tap, as you would in a car with your steering wheel, okay. And you apply two forces, you're driving the car, okay, you apply two forces, one down, one up, and it causes a turning effect only, okay, a turning effect. You're applying a linear force down, linear force up, because there's a fulcrum in the middle, you get a turning effect, okay. It's really a case of learn the definitions, understand what's going on, be able to apply this across to the experiment. After midterm, we'll be looking at some nice little questions on it, but for the time being, we're very happy with that. We're in good shape at that stage, okay? That's moments, right, and turning forces. The other thing we want to look at now is power, very briefly. Okay, so power should really have been included earlier, but just to be very clear on the idea, okay, remember, power is work over time. Now we've done this time and time again, and we will be coming back to it in heat in detail, but I just want you to make sure you're happy with it. Power is work over time. Okay, so work is joules divided by seconds, so joules per second, and that's watts. But remember the crucial point, and we've said this so many times, okay? If you ever see something called 40 watts, okay, if you have a 40 watt bulb, okay, that's telling you that 40 joules per second. So every time you see the word watt, you read it as joules per second. That's joules per second, 40 joules every second. So a 40 watt light bulb is telling you that electrical energy is being converted into other forms at the rate of 40 joules every second. That's it. That's what it means, right? No, it might all be converted into light energy, there'll be heat and so on as well, but that's what 40 watts means, okay? A 3 kilowatt heater is converting 3,000 joules of energy per second from electrical energy mainly into heat energy. Okay, mainly into heat energy. That's it. That's power. So I think we're happy with that. We'll be doing a lot of it in the heat experiments or the heat calculations after later on in the week or after midterm. All right, there you go.